No.
Okay, more partial differential equations. I just want to emphasize that we're going to be using two books for the rest of the semester, the book by Farlow that we started with, and the book by Logan, Applied Partial Differential Equations, which I put onto the website for the course and which you can also get for free as a free download through the Lehman College Library. Or you can always buy the book if you want, but you certainly don't have to. Questions about anything?
Hi, Professor.
Yep.
I guess I did a meditation thinking about how mathematics works, because right now this is a physics class. Sometimes I get confused how the equations in mathematics apply to the physics. Can you explain more about this subject, because it's brand new? How to model an equation to interpret a natural phenomenon.
Okay, so so this is exactly what is discussed in chapter 1 of this book by Logan. And part of your assignment for next week is to begin to read the chapter and work on some problems. So we're not talking about physics in this class, but it is a fact that many partial differential equations arise in problems in physics. So for example, for us, we're starting with the differential equation, which has to do with the diffusion or the flow of heat. And so our picture is, we have a metal rod which conducts heat. And let's say it has length 1. And at time t equals 0, there is the initial condition of temperature. So U of xt is going to be the temperature at position x in the rod at time t. And so at time 0, U of, let me just double check one thing. U of x0, this is just the initial distribution. This means time t equals 0, there's some temperature at the rod, which we can call, I don't know, phi of x. So this is the initial condition. This is the time, at time t, the temperature. There's also a boundary condition. So for all t greater than or equal to 0, the temperature at the boundary means the ends of the rods. So U at position 0 at time t is something, G1 of t, and U at the end of the rod, 1 at time t, is some other function of t. And the question is, the problem is, describe U of xt, or compute u of xt, or understand this function. And we're given, or we're told, that the heat in this rod satisfies a certain partial differential equation, which is sometimes called the diffusion equation or the heat equation, which says that the partial of u with respect to t is some positive constant alpha squared times the second derivative of u with respect to x. So this is our PDE. And on the one hand, this comes up as a model for this problem in physics. On the other hand, from the point of view of mathematics, this is completely irrelevant. You can just say, here's a mathematical problem. Find a function of two variables, t and x, which satisfies this differential equation and also satisfies this initial condition and these boundary conditions. Now, it just turns out that many problems in physics lead to the solution of many problems in physics requires solving some partial differential equation. But that's just the origin of the problem. From the point of view of mathematics, we just want to solve the problem. Where it comes from is not particularly important. Okay. So this is a mathematics class. We don't have to worry too much. We don't have to worry at all about the physics. The problem is always, here's a differential equation, a partial differential equation. It satisfies, we're given some initial condition and some boundary conditions. Find a function or find all functions that satisfy the differential equation, the initial condition, and the boundary conditions. I mean, that's, and for many reasons, this particular differential equation is a very beautiful equation to study, and that's what we're doing. But for more discussion of this in more depth, you have to begin to read the first chapter in the book by Logan, which goes into more, has more examples and more details than what I've just said.
So when the equation is equal to 0, is homogeneous. So all the type of problems involve. I mean, it's a parabolic solution.
Well, I mean, you're using words that are not important to us. We don't have to use the word parabolic. It's irrelevant. This is just a particular differential equation. You don't have to give it a name in order to solve it. The problem is to try to solve this equation. Okay. And in this equation, you don't have to worry about homogeneous, non-homogeneous. We're not even talking about that. I mean, this may be a parabolic equation, whatever that means, but for us, that is not relevant to anything. The question is, how do we solve the equation? And in the particular case, when the boundary conditions are 0, so we have our rod, and suppose when x is equal to 0 and when x is equal to 1, the temperature is fixed at 0 for all t. And now what we would expect, if this problem models the physical problem, we expect that u of xt goes to 0 as t goes to infinity for all x from 0 to 1. Because if we fix the temperature at the ends to be 0, you have some initial temperature, phi of x equal to u of 0, u of x comma 0. You have some initial temperature distribution, but if there's no heat entering or leaving the rod along the length of the rod, if it's an insulated rod, and if the temperature at the ends is kept at 0, you expect if phi of x is greater than 0 at some point, at that point that the rod will cool to 0. If it's below 0 at some point, you expect the rod to heat up to 0. You expect the limiting behavior to be just the 0 function. That's what we would expect if this differential equation really does model the rod. Suppose we had something different. Suppose we started with an initial condition where at the left end of the rod, the temperature was kept constant, sorry, a boundary condition. Suppose the temperature was K1 at the left end of the rod, and at the right end of the rod, it was some temperature K2. What we would expect to happen over time. So this is temperature, this is X. At X equals 0, the temperature, this is, the temperature is 0. So the temperature is K1. At the other end of the rod, the temperature is K2. What we would expect to happen to the temperature along the rod as time increases? Well, you might expect that, for example, if K1 and K2 are different numbers, if K1 and K2 are the same, you would expect the rod just to approach that constant function, the constant value K, the temperature to approach K. You might expect it just increase linearly. So you might expect that the limit as t goes to infinity of u of xt would just be the straight line from K1 to K2. What is the equation of the straight line? It's y equals the slope, K2 minus K1, x plus K1. This is the equation of the line. When x is equal to 0, it's K1. When x equals 1, it's K2. You would expect this to be equal to K2 minus K1x plus K1. If you think the physics leads you to a thermal equilibrium, which is just a linear increase in temperature as you go along the rod from the left to the right. Right? So interpreting the problem physically sometimes gives us some intuition about what the solution should look like. Or alternatively, if we know what the solution should look like, this gives us some additional constraint on the mathematics that we do. And we'll see that in a moment. Okay. And I'm going to start by repeating exactly what I did on Monday, because it is an extremely important method to solve a differential equation, which is called separation of variables. So this is different from separation of variables for an ordinary differential equation. So this is a method to try. So we have our partial differential equation. The derivative of u with respect to t is some positive constant times the second partial derivative of u with respect to x. So the rod has length 1, and time goes from 0 to infinity. And let's start with the boundary condition that at the ends of the rod, the temperature is always 0. So u of 0t and u of 1t equals 0 for all t. And suppose we have some initial condition that at time 0, the temperature at position x is some function phi of x. So we want to try to solve this equation. And so we shall assume and see what happens that our function u of xt can be written as a product of a function of x and a function of t. That is, you can separate the variables in the solution into a product of two functions. So if we differentiate with respect to t, this is a constant with respect to t. This is the derivative, t prime of t. And if we take the second partial of u with respect to x, that's differentiating this twice with respect to x, and this is constant with respect to x. So if we plug this into our partial differential equation, we get x of x, t prime of x equals alpha squared x double prime of x t of t. And we can put all the t's on one side and all the x's on the other. This is t prime of t, all right, over alpha squared t of t equals x double prime of x over x of x. So if you can separate variables, you have this relation. This is a function of t, this is a function of x. For these to be equal means that these are constant. This is k, right? Because this means fix some x. For that value of x, this is equal to k. For all t, this equals k. Similarly, for any t, this is equal to this particular value of t for all x. So this also has to be a constant. They're the same constant. All right. Are there any questions about this? This is really the fundamental step. So this leads to two. Yes.
Yeah,
Question?
yes, when you talk about boundary condition, you refer to the limit.
I'm sorry, when I talk about what?
When you're talking about boundaries condition.
No, the boundary of the rod are the two ends of the rod. So for this rod, the boundary is at x equals 0 and at x equal to 1. So if I'm told something about, for example, when x is equal to 0, my boundary condition is the temperature at this end is 0 for all time at this boundary point. At the other boundary point, when x is equal to 1, u of 1t is also equal to 0. So this is my boundary condition, that for all time at the boundary, the temperature is 0.
Okay.
So this gives me two ordinary differential equations. T prime of t equals k alpha squared t of t, and x double prime of t, x double prime of x, excuse me, equals k x of x. Now, we can solve this differential equation. This differential equation has the solution e to the minus k alpha squared t. Sorry, e to the k alpha squared t. This is the world's simplest ordinary differential equation. T prime is some constant times t. Now, if k is positive, then t of t goes to infinity. If k is 0, then t of t is constantly equal to 1. But we expect, or we only want to find the solution where t of t goes to 0 as t goes to infinity. The only way that can happen is if k is negative. So we can write k as minus something positive, which I write as minus lambda squared. So for some positive number lambda, this k is minus lambda squared. So t of t is equal to e to the minus lambda squared alpha squared, that's like lambda alpha all squared times t. So if we separate variables, the time component has to be a decaying exponential that looks like this. Okay. Now, what about the function capital X? So we have x double prime is k, which is minus lambda squared x. And we know the solution of this equation is x equals a times the sine of lambda x plus b times the cosine of lambda x. Okay. So u of xt, which is t of t x of x, is e to the minus lambda alpha squared t times a sine lambda x plus b cosine of lambda x. So if we separate variables, a function of this type will always satisfy the differential equation. Okay. Questions about this? Okay. But we must also satisfy the boundary condition. So we have to satisfy that u of 0t equals 0. Now, what happens when you plug in x equals 0? You get e to the minus lambda alpha squared t times a sine of 0 plus b cosine of 0. Sine 0 is 0 and cosine 0 equals 1. So this is b e to the minus lambda alpha squared t. So this has to equal 0. Now, an exponential is always positive. So the only way this can be 0 is if b equals 0. So immediately we find that b has to be 0 for any solution that satisfies one of our two boundary conditions. So u of xt can only be of the form a e to the minus lambda alpha squared t sine lambda x. Right. All right. What about the second boundary condition? So the second boundary condition is that at the end, when x is equal to 1, the temperature is also always 0. And when you plug in x equal to 1, what do you get? You get a e to the minus lambda alpha squared t sine of lambda. So that has to equal 0 for all t. Now, again, this is positive. So this means that a sine lambda has to be 0. Now, there are two cases. Could be a is 0, and in that case, u of xt is 0 for all x and t. So if a is 0, the only solution is identically 0. So unless the boundary condition is always 0, this won't work. And the second case is a is not 0. And in that case, sine lambda equals 0, which means lambda is plus or minus a multiple of pi. You can't have lambda equals 0 because then the function would be 0. So lambda is just plus or minus pi, 2 pi, 3 pi, and so forth. So u of xt is a function of the form a e to the minus plus or minus n pi alpha squared t times the sine of plus or minus n pi x. Sine of plus n pi and minus n pi are the same because, sorry, not the same. They differ by -1. That just changes the constant. So let's just call this u sub n. For every positive integer n, there is a solution that satisfies the boundary conditions. Now, we have u sub t equals alpha squared uxx is a linear equation. What that means is that if u1 and u2 are solutions, then if I take any linear combination of u1 and u2, this is also a solution. So it follows that if I take any sum of functions un of xt and going, let's say, from 1 up to capital N, this is a solution. And it turns out also that if your function are nice, you can actually make this an infinite series. So why is that important? Well, I proved that every one of these functions satisfies the differential equation, and every one of these functions also satisfies the boundary condition, but I also have to worry about the initial condition. The initial condition is that u at time 0 is some function phi of x. Now, what is u sub n at time 0? When I plug in t equals 0, e to the 0 is 1. This is just some constant times the sine of n pi x. So what I want to do is express the function phi of x as some series of these functions that I know are solutions, a sub n sine of n pi x, and goes from, let's say, 1 to infinity. Now, a series like this is called a Fourier series. It's an example of a Fourier series. In general, you would allow sines and cosines both. And so does this mean we've solved our problem? Well, no, unless we have a way to write phi of x. If you can express phi of x as a series of this form for some choice of the coefficients a sub n, then in fact, you've solved the problem. You've solved the differential equation with the boundary condition and with the initial condition. So if phi of x is the function which is nice enough, whatever that means, so that you can express it as a Fourier series, then in fact, we have solved our initial value boundary value problem. So we have the following problem in Fourier series. Given phi of x, compute what we call the Fourier coefficients, a sub n, such that phi of x is a sum from 1 to infinity of a sub n sine of n pi x. Now, how do we compute these coefficients, a sub n? So must know simple trig identities. So in particular, there is the addition formula for the cosine. Cosine of a plus b is cosine a cosine b minus sine a sine b. That's the addition formula for the cosine. And the cosine of a minus b is cosine a cosine b plus sine a sine b. So if you subtract these equations, this minus this, you get 2 sine a sine b is the cosine of a minus b minus the cosine of a plus b. Or if you like, sine a sine b is a half cosine of a minus b minus cosine of a plus b. Okay. Any questions about this? Okay. Well, suppose we let a equal m pi x and b equal n pi x. So what we get is that the sine of m pi x times the sine of n pi x is 1/2. See, when we subtract, you get the cosine of a minus b, that's m minus n pi x, minus the cosine, let's see, when you add, you get m plus n pi x. Okay. So if I've done my arithmetic correctly, which sometimes I do and sometimes I don't, we have this trig identity. So
Professor, the reason you're using those formulas, the three formulas, you need to add more than one equation. What is the reason?
well, the reason is I want to figure out a method to compute the Fourier coefficients, right? So I can solve the differential equation that I started with if I can find numbers an, so I can write phi of x as this sum of sines. I want a method to compute a of n, a sub n. That's my goal. So this is, to get there, this is a little trigonometry digression. Okay. So what I've just shown is the following trig identity. The sine of m pi x times the sine of n pi x for any integers m and n is 1/2 cosine of m minus n pi x minus a half, I'm just multiplying by a half, cosine of m plus n pi x. Right? This is my identity. And I'm going to integrate this from 0 to 1. Okay? I want to find this integral. Now, I know the integral of the cosine is the sine. So let's look at two separate cases. So if m is equal to n, I'll just call this left-hand side. My left-hand side, if m equals n, this is 0. The cosine of 0 is 1. This is 1/2 the integral of 1 dx minus a half the integral from 0 to 1 of cosine of 2m pi x dx. The integral from 0 to 1 is 1, is x from 0 to 1 is 1. So this is a half minus, let's see, m equals n, not equal to 0. So the integral of cosine 2mx is 1 over 2m pi sine of 2m pi x. Evaluated from 0 to 1. This is 0 at 0 and 0 at 1. So this term is 0. So I have a half minus 0 is a half. So if m is equal to n, different from 0, this integral equals a half. If m is not equal to n, what do we get? The left-hand side, when I integrate this, this is 1/2. I get 1 over m minus n times pi sine of m minus n pi x from 0 to 1 minus a half 1 over m plus n pi sine of m plus n pi from 0 to 1. This is all equal to 0. So this is what is called sometimes one of the orthogonality relations for the sine. The integral from 0 to 1 of sine m pi x sine of n pi x dx equals a half if m equals n and 0 if m is not equal to n. This is for m and n positive integers. Right? Okay. So we have this orthogonality relation, which is so important. I will write it down again. So mn positive integers, the integral from 0 to 1 of sine m pi x sine n pi x dx equals a half if m equals n and 0 if m is different from n. All right? And why is this important? So we want to find these Fourier coefficients a sub n such that my function phi of x is summation a n sine n pi x. And using the orthogonality relation, I can find a formula for a n. Suppose I take phi of x and I multiply it by sine mx, m pi x. So this is summation a n sine n pi x sine m pi x sine n pi x. I just multiply through by this number. And then I integrate from 0 to 1. Now, in analysis, it's hard to know when you can interchange summation and integration. But one can prove if phi of x is a nice function, if it has enough, even just 2 or 3 times continuously differentiable, you can interchange summation and integration. You can write this as summation n goes from 1 to infinity, a n integral from 0 to 1 of sine m pi x sine n pi x dx. And what do we know about this integral? It's 0 unless m equals n. So if n is different from m, this is 0. And if n equals m, this is a half. So this is a half a sub m. In other words, I've now computed am. Am is equal to 2 times the integral from 0 to 1 of sine m pi x dx. So phi of x is nice continuously differentiable function, smooth function, very pretty function. I now have a formula for the Fourier coefficients.
Professor,
Yeah,
can you just go over the last part again, what you said? Because at first it says a of n and then it becomes a of m.
doesn't matter. This is for any m. M1, 2, 3, n. So it doesn't matter, right? This is just a letter. It just stands for a number. What is A3? 2 times the sine of 3 pi x dx. I mean, this is exactly the same as saying, all right, if this is true for all m, that's the same as saying that an is 2 times the integral from 0 to 1 sine of n pi x dx. So phi of x is summation an sine of n pi x. It's this Fourier series. Oops. Yeah, phi of x. I left out the phi. So AMM is so AN is phi of x times the sine of n pi x dx. That's what A of AN is. So phi of x is this Fourier series. And U of xt, the solution to my problem, is e to the minus let me just go back and find it here. That's my solution.
Professor, can you explain why you're using the summation notation here? It's just for exclusive for coefficients?
Well, so what we saw is, so this is a review. For every positive integer n, the function u sub n of xt equals e to the minus n pi alpha squared t sine of n pi x is a solution of the partial differential equation that satisfies the boundary condition that u of 0t and u of 1t equals 0. If you let x equal 0, or if you let x equal 1, you get 0. So for every n, this is a solution of the equation. But I also have to set, which means that if I take an un of xt and sum over n, this is also a solution. But we have to satisfy the initial condition. So you must find numbers a sub n such that summation n goes from 1 to infinity, an u sub n of x comma 0 so u sub n of x comma 0 equals the initial condition that when at time t equals 0, u of xt is phi of x. And how do I find these coefficients? Well, they're given by this formula. An is 2 times the integral of phi of x sine n pi x. So that tells me what the ANs are. And yeah. All right, so let's look at a very simple example. So suppose the initial condition is that phi of x, that means the temperature when the time is 0 at position x, that's this function phi of x, is just given by sine pi x plus a half times the sine of 3 pi x. So this is a Fourier series for the function. So you can think of this as that phi of x is a1 sine pi x plus a2 sine 2 pi x plus a3 sine 3 pi x plus a4 sine 4 pi x, and so on. But a1 equals 1. A2 is 0. There's no sine 2 pi x. A3 is a half. A4 is 0. And so is A5, A6, and so forth. So this is the Fourier series of a function, of the function. And it only has 2 terms. It's simple. So u of xt, there's the term when n equals 1. N equals 1, e to the minus pi alpha squared t times, times 1. Sine of pi x plus 1/3 e to the minus 3 pi alpha squared t sine of 3 pi x. So I claim this function satisfies, oops, sorry, this is a half. I claim this satisfies everything. Let's check. What is the partial of u with respect to t? If I differentiate with respect to t, I get minus pi alpha squared e to the minus pi alpha squared t sine pi x plus minus 1/2 3 pi alpha squared e to the minus 3 pi alpha squared t sine of 3 pi x. Right? If I differentiate this with respect to t, if I take the partial derivative with respect to t, this is what I get. What do I get if I differentiate with respect to u? Partial of u with respect to x is pi e to the minus pi alpha squared t cosine pi x plus 1/2 times 3 pi e to the minus pi alpha minus 3 pi alpha squared t cosine of 3 pi x. And when I take the second derivative, I get a minus pi squared e to the minus pi alpha squared t sine pi x. And I get a minus 3 pi, so minus 3 pi squared times a half e to the minus 3 pi alpha squared t sine of 3 pi x. If I multiply this by alpha squared, I get this.
What about the sine 3 pi and turn once you have to do that multiply by x through?
So alpha squared times this, I might be off by a minus sign. I'm not sure why. Oh, no, that's right. Exactly. So partial u with respect to t. So just compare. This equals this. Partial u with respect to t equals alpha squared, second partial of u with respect to x. So this is a solution of the differential equation, as of course it has to be. Let's check the initial conditions and the boundary conditions. What about the boundary conditions? U of 0 t, when you let x equal 0, you get 0 plus 0 equals 0. U of 1 t, when you let x equal 1, sine pi and sine 3 pi are both 0, you get 0. So the boundary condition is satisfied. What about the initial condition? What is u of x comma 0? When you let t equal 0, these are both 1. You get sine pi x plus a half sine of 3 pi x. That's exactly the initial condition that I had to satisfy. So it works. Okay. So any questions about this? Let's do a practice problem. Let's compute the Fourier sine expansion for the function phi of x equal 1 for x between 0 and 1. So this is the graph of the function, just the constant function 1. So we want to write 1 as summation, n goes from 1 to infinity, a sub n sine n pi x. Well, how do we do that? Well, we have a formula for the Fourier coefficients. So for the Fourier coefficients, an is 2 times the integral from 0 to 1 phi of x sine of n pi x. But our function phi of x is 1. So an is 2 times the integral from 0 to 1, just sine of n pi x. What's the integral of the sine of n pi x? It's minus 2 over n pi cosine of n pi x from x equals 0 to x equal 1. Right? Does that look okay? When x equals 0, of course, this is 1. What is it when x equals 1? So let me just write this. This is minus n over n pi minus 2 over n pi cosine of n pi x equal 1 minus the cosine of 0. What is the cosine of n pi equal to? Can someone tell me? What's the cosine of pi?
1 or negative 1.
Sorry?
Cosine of pi is negative 1.
What's the cosine of 2 pi?
1.
What's the cosine of 3 pi? What's the cosine of 3 pi?
Minus 1.
What's the cosine of 4 pi?
1.
What's the cosine of n pi?
Negative 1 raised to the n.
This is
power.
minus, it's minus 1 to the nth power, minus 1. If n is even, this is plus 1. Plus 1 minus 1 is 0. So this is equal to 0 if n is even. If n is odd, this is minus 1 is minus 2. Minus 2 times minus 2 is 4 over n pi if n is even. So what we have is that 1 is summation, n goes from 1 to infinity, an sine of n pi x, but an is equal to 0 if n is even. Sorry, I should say odd. And equal to 4 over n pi if n is odd. So this is summation 4 over n pi, but only over the odd numbers, sine of 2 pi x, sine of n pi x. So when n is 1, you get 4 over pi sine pi x plus 4 over 3 pi sine 3 pi x plus 4 over 5 pi sine 5 pi x, and so on. Okay. Now, it's actually one of the homework problems. It's number 3 at the end of this chapter. to actually calculate this Fourier sine expansion. And then you should use your computer or your calculator, whatever you have, just to draw the first few terms and just see how closely this approximates the constant function 1. Let's see. If you just look at the first term, sine of 4 over, sine four over pi, sine of pi x from 0 to 1 it looks like that. If you were to look at 4 over pi sine pi x plus 4 over 3 pi sine of 3 pi x, so it looks like that. It's getting closer to 1. And it's really interesting to use your computer to actually graph the first 3 or 4 or 5 terms of this Fourier series, just to see this miraculous thing that somehow adding these sine functions gives you something which is approximating the constant function 1. It really is valuable exercise. Right? So this really I encourage you to do. If you know Maple, you can always download Maple for free from CUNY, right? I mean, you can buy it for hundreds of dollars, but if you're a student at CUNY, you can get Maple for free. If you have any kind of graphing calculator, you can also just use that, but the pictures aren't as good. But it really is a worthwhile exercise to figure out how to do these things, just to look at the pictures that you get. Okay. Okay. Let's go on a little bit further. Up to, it seems, page 13. So we've been looking at this equation u sub t equals alpha squared uxx. And we typically had a boundary condition, which was u at 0 t equals 0 and u of 1 t equals 0 for all t. So in our rod, in the example we've been looking at, we've always been fixing the ends to have constant temperature 0. So suppose we change that. Suppose that the boundary conditions now are there's a constant temperature at each end of the rod, but at the left end, when x is 0, the temperature is somehow fixed at K1. At the right end, the temperature is fixed at K2. And let's say K1 is different from K2. Now, This makes things much more complicated to solve, but there is a trick, if you like, or a method to somehow reduce this to the case where we have, and let's say our initial condition is that u of x comma 0 is some function phi of x. So this is our initial value boundary value problem for this diffusion problem. And what we can say is, well, we think, or our intuition is, or we're told that in the final solution, as t goes to infinity, u of xt approaches just the picture we drew before, the straight line distribution from k1 to k2. What's the equation of the straight line? By the point slope formula, y is equal to the slope k2 over k1 times x. That's actually just the slope in it, plus k1. Oops, x minus 1. Oops, sorry, yeah. Slope is k2 minus k1 times x plus k1. The book looks at this in a slightly different situation where, let's just suppose the length of the rod now is L. So this goes from 0 to L. So this is L. Slope of the line is k2 minus k1 over L plus k1. Okay. So we expect that u of xt approaches k2 minus k1 over L x plus k1 as t goes to infinity. And in fact, you can check that if you let u of xt equal this, when x is 0, you get k1. When x is L, you get k2. This satisfies the boundary conditions. And so we can say, okay, let's change variables if we like. Let u of xt be equal to this expression, k1 plus, this is the way the book writes, it's exactly the same thing, x over L, k2 minus k1, plus some other bit, u of xt. So this is what we think of as the steady state solution. And this is some transient quality, which we expect goes to 0 as t goes to infinity. So in any case, we say, let's look for a solution of this form. And now let's translate this into our differential equation. Let's look at a differential equation which is satisfied by this function. Okay. If we differentiate with respect to t, the partial of little u with respect to t, this only depends on x, is the same as the partial of capital U with respect to t. What is the partial of u with respect to little x? When you differentiate with respect to little x, this is 0. This is k2 minus k1 over L. plus the partial of u with respect to x. And when you differentiate a second time, the derivative of a constant is 0. This is a little u. Is the second partial of big U with respect to x. So what we get is that the partial of capital U with respect to t, which is the partial of little u with respect to t, which is alpha squared times the partial of little u with respect to x twice, is alpha squared times the partial of capital U with respect to x twice. So u of xt and little u of xt both satisfy the partial differential equation that we're interested in. What about the boundary conditions? What is u of capital X comma 0? Sorry, u of 0 comma x. So u of 0x, remember, u of xt is little u of xt minus k1 plus x over L, k2 minus k1. So when you let x equal 0, sorry, when you let, for the boundary condition, u of 0 comma t, when you let x equal 0, you get u of 0 t minus k1, but u of 0 t was k1. This is k1 minus k1 is 0. And u of 1 comma t, that's little u of 1 t, minus, what do you get when you let x equal 1? Sorry, when you get x equal L, k1 plus k2, you get k2. This is k2 minus k2 is 0. So this new function, capital U, satisfies the homogeneous boundary condition that the temperature is 0 at both ends. And what about the initial condition? So u of x comma 0, when you let t equal 0, that's u of little x comma 0 minus, there's no t1 there, that's okay, k1 plus x over L, k2 minus k1, u of x comma 0 is phi of x minus this linear term. So this is some new function which we could call phi bar of x. So if I make this change of variables, I end up with the same partial differential equation, but now with homogeneous boundary conditions and a new initial condition, but the initial condition is only this linear perturbation of the original boundary condition. Okay. So this is a method to convert a non-homogeneous boundary condition to a homogeneous boundary condition. It's a very simple technique, but it works when the ends of the rod are fixed at a constant temperature. So what I've just done is discuss a little bit of the beginning of lesson 6 in Farlow. And there is, I think, a lot of meat, a lot of mathematical content to this discussion. And you really do need to spend a fair amount of time, I think, studying this material. And you'll get a deeper understanding of what's going on as well as you look at the book by Logan. Okay. Any questions about this? All right.
At what page it is located?
This is lesson 6 in Farlow. which is like chapter 6 in Carlo.
And the homework,
I just posted the homework for this week, for the next 2 weeks on Blackboard, and I sent everybody an email with it as well. So just check your email or check Blackboard. And it has the homework for next Monday and the Monday after that.
and for the Exxon one, results this
Oh,
week.
I'll post it by the end of the week. You'll see it on Blackboard when the exams are graded. Okay. Any other questions for today? All right. Again, there's a lot to learn. Maybe if you study chemistry or physics, you've seen some of these types of problems before, but having seen it before is not a prerequisite. Okay. All right. Have a good weekend, everyone. We'll be back next Monday. Bye.
Thank you.
Take care.